Hello and welcome to our webinar on tips on teaching chemistry for the IB Diploma with Dr. Steve Owen. I'm Tamsin Hart from Cambridge University Press, and I'll be hosting this webinar for our speaker, Steve. Thank you for joining us today. I'm just going to give attendees a little time to join the webinar before we start. If you'd like to chat to one another and let us know which country you're joining us from, please feel free to use the chat box. It'd be great to hear from you. While you're waiting, I'm going to launch a poll to find out about your main challenges in the classroom. It would be very interesting to see what answers we get. If I haven't included your main challenge, you can add this to the chat and see if your fellow attendees have similar challenges. You should be seeing the poll on screen now. So thank you for joining us for our webinar on tips on teaching chemistry for the IB Diploma today. I'm Tamsin Hart from Cambridge University Press, and I'll be hosting this webinar for our speaker, Dr. Steve Owen. While we wait for more attendees to join us, let me explain how we're going to run the webinar. We're recording the webinar today to share with you afterwards, so don't worry if your internet drops out, just rejoin us when you can. If you're having trouble with your speakers, we suggest using headphones or checking that your speaker isn't muted. Your microphones will remain muted throughout the webinar. If you have any technical issues or questions about our science products, please can you put those in the chat box, and my colleague Georgia Robinson and our commissioning editor Michaela Inthurst will be on hand to help you. Please can you put any questions for Steve into the Q&A box, and our speaker will answer those at the end of the webinar. 7 days after the webinar, we'll send you an email thanking you for your attendance with a link to the webinar recording and information on where to find your webinar slides. Unfortunately, we can't provide certificates. However, you can use this email as proof of your attendance. Okay, that's the end of our introduction. Just before handing over to Steve, I'm just going to take a look at the poll and see how we're going. I can see 75% of you have participated. So I'm just going to give you a couple more minutes just to see if you want to take part and tell me on the poll on your screen what your main teaching challenges are. And as I said, if there are some challenges on there that we're not getting, we'd love to hear about those in the chat. Okay, we're having a really great participation rate here. So I think I'm going to give you one more second. Brilliant. And then end the poll there. Okay, and share the results. Let's have a look what the main challenges are. Okay, so coming out on top is handling syllabus changes with 53% of you are finding that's a challenge. Then following that, 47% teaching with technology. You all have that issue. Then a couple of ties here, 32% planning my lessons and applying effective teaching approaches. Next one, we've got preparing my students for assessment. And after that, 21% of you both find lack of time and time management and supporting my English as a second language learners a challenge. And at the end there, we have 11% of you find following IB Diploma approaches a challenge. Thank you so much for participating in the poll. Those are some very interesting results. And thank you very much for joining the webinar today. Now, let me hand over to Steve.
Thank you for that, Tamsin, and welcome everybody to the webinar. My name is Steve Owen, and I've been teaching IB chemistry for about 26 years now. And I'm going to talk mostly today about the changes to the IB syllabus. Obviously, a new IB syllabus was published around about February. Hopefully most of you have had a chance to have a look at the syllabus already, but I'm just going to talk about a few of the challenges perhaps in delivering that new syllabus. And first of all, let's just have a look at what has changed, first of all, with regard to assessment. Of course, one of the big things now on this new syllabus is there are no options anymore. And I must admit, I'm not too disappointed with that. Although there was some quite nice chemistry in the options, I think it did make assessment quite challenging because there are obviously quite big differences between the options, and getting questions which were sort of the same standard between the different options was quite a challenge. And because obviously there are no options. That means that we're down to 2 papers for the exams. Paper 1 is divided into paper 1A and paper 1B. Paper 1A is very much just the old multiple choice paper. And paper 1B is something new. It's very similar to, I think, section A of paper 3 at the moment, which is database questions, practical based questions. And this could be a real challenge. I must admit, the section A of paper 3 is something that my students are not overly keen on. They can be quite difficult questions to figure out what is required and everything. So I think this will require quite a bit of practice over the 2 years in preparation for the first exams on this syllabus. Paper 2 then is back to very much is the same as what we've got basically at the moment. So answer on the question type questions. Then one big change in the assessment is that the students can use a calculator and data booklet for all the papers. And we'll have to see how this pans out a little bit with the questions. So hopefully we don't get too many involved calculations or questions in the multiple choice where students have to flick through the data booklet, because it's actually quite tight for time in the multiple choice and everything as well. But we'll see how that pans out as we get more exams. So let's have a look at some of the differences in content. And first of all, what's been removed. And apart from the options, not huge amounts really. There are a few things which have come out. So for instance, ppm, the calculations involving that. I don't think it was a major part of the previous syllabus, and the students did find it quite difficult for some reason. So so that has gone, which will be a relief to some people. It was quite nice though at times. It allowed you though to talk a bit about environmental issues, concentration of CO2 in the atmosphere. And then there's a bit of organic chemistry gone again, which I must admit to being quite disappointed with. It's organic chemistry was the thing when I was 16, 17, 18. This was the thing that made me want to go to university to study chemistry. And so it's a shame that's there's a bit less content of that, but there's still a few mechanisms there. So there's still some interesting organic chemistry. So hopefully that will help with getting the students hooked on chemistry and them taking it up in university as well. And then let's have a look at what's been added. And there are quite a few things that have been added. Obviously, with one without the options, then they've got to put more stuff into the core materials. So some of it is stuff which is just coming in from the old syllabuses, where we've had sort of previous incarnations of the syllabuses. Things like buffer calculations are back in. They were on the options before, but they're back into the main part of the course. Calculations involving enthalpy change of combustion are mentioned explicitly. There's a bit more on delta G. There's a few things from the options, especially from options A and C. Things like bonding triangles are in. Condensation polymerization is back into the syllabus as well, and that will be something I will talk about in a little while as well. So there are quite a few changes to the content in there, but most of it is very much the same as on the previous syllabus. So let's have a look at the setup for teaching. So on the IB syllabus, there are basically 22 sections, and which is a change from last time. Before we had sort of 11 sections, now we've got 22. And the material is split up in various ways in those sections. So some of the sections are very much the same as we're used to, but some of the material is also split up between multiple sections and occurs in some slightly strange places at times as well. So, but we'll have a talk about that as we go through. So if we take the 22 sections, what I've done here is I've divided them up into, on the left, we've got the qualitative material, bonding and atomic structure, etc. On the right, we've got the quantitative material. And the school I'm at, we tend to split the high level teaching between 2 teachers. So basically one of them does the qualitative, one does the quantitative. That might not be possible for all of you. But standard level, we teach all together. So this is basically sort of, this would be my sort of track through the syllabus here in order, and but we can group together some things according to sort of the previous topics as well. So for instance, now bonding is, whereas it was in one section before in the previous syllabus, is now in 4 separate sections, but it just follows through quite nicely, so there's no real controversy there. The organic chemistry is split up a bit though, and I'll talk a little bit about that and some of the challenge with delivering the organic chemistry there in a minute. Moles again is split up. I'll talk about that a little bit in a minute as well. And then we've got energetics and most of the other things. The names are a bit different for these sections, but basically the material is very much the same: rates, equilibrium, acids, and redox. So let's have a look where we teach certain topics. So first of all, if we start off with moles or stoichiometry, before this was all together, and now this has been split up quite a bit. So in section 4 of the syllabus, this starts off with an introduction to moles, looking at how we work out the amount in moles of using masses, volumes, concentrations. But then it goes into Avogadro's law and working things out using Avogadro's law. Then in section 5, in the next section of the syllabus, we're into ideal gases and the gas laws. And then all the way then further on in chapter 16, this is where the sort of moles calculations start coming in, where we've got mole ratios using equations to work out the number of moles of certain things. So it's a slightly odd way of arranging it, and especially with Avogadro's law in there, where Avogadro's law comes at the end of section 4, where at that stage they haven't done mole ratios, they haven't done ideal gases if you're following the syllabus linearly. So I think my approach to teaching the stoichiometry, the moles part of the course, will be very much to put it all together, teach it very much as I have done, so introducing mole ratios earlier, introducing perhaps ideal gases before I'm teaching Avogadro's law. And I think that will be an easier way of sort of teaching the material. But I suppose the new syllabus gives us opportunities to think again about how we do things and perhaps come up with some new ideas and new approaches to teaching as well. So there may be some merit in teaching it as it is on the syllabus as well. The other thing I was going to look at, is the periodic table. Now, I'm actually an inorganic chemist, so the periodic table is very close to my heart. And the question is where to teach the periodic table. In various previous syllabuses, we've either had the periodic table before bonding, we've had the periodic table after bonding. And there are good cases for putting it in either of those places. It relates to both, so it can be done before or done after bonding. And of course, it's also involved in the atomic structure, electron configuration stuff. So there are lots of different places it could be taught. But where I actually teach it is, I actually teach it right at the end of the course. I tend to use it very much as something to pull a lot of the other material together. I do introduce it early on. I do introduce it when I'm talking about the atomic structure, and of course teaching students how to work out electron configurations from the periodic table. But the main part of it is I like to come back to right at the end of the course, partly through revising some of the atomic structure, and partly just through trying to bring everything in together, sort of talk a little bit more about things like bonding. So if you look at the oxides, so for instance, the structures using VSEPR, Lewis formally as well in there. So bringing everything together at the end of the course. And this is especially, I think, the case when we're looking at the transition elements part of the periodic table topic. And don't worry about all the writing on the screen there. There's quite a lot of it. But the transition elements are mentioned in about 5 different sections of the syllabus, starting off with, first of all, the formation of coordination bonds, then delocalized d electrons in the section on metallic bonding. Then we get into the sort of the main thrust of transition elements in section 10, which is the periodic table section. Then we come on to things like redox and oxidation states and Lewis acid and base theory connected to the transition elements. So again, for me, I like to teach this right at the very end, sort of bring lots of things together to talk about catalysis, talk about changes in oxidation state, and also I'm a transition metal chemist. It's my speciality, and I like showing quite a few demonstrations towards the end of the course as well. So by the end of the course, it's the students are getting quite, so we're getting close to the exams. It's getting a bit more stressful, and it's nice to have a nice few fun demonstrations involving transition metals as well. So some pretty colors and everything. So I think the periodic table fits in nicely at the end of the course. But yeah, obviously there are other ways of teaching it as well. And another argument in terms of doing it at the end of the course is in terms of the oxides. This is a part we're used to from the previous syllabus, where we're just showing the variation from basic oxides of the left-hand side of the periodic table through amphoteric to the acidic oxides over the right-hand side of the periodic table, which is fine. That would fit in fairly much anywhere. But then this syllabus goes on to talk about acid rain and then ocean acidification. And I think these are very difficult topics to talk about if the students haven't already looked at equilibria, they haven't looked at the Chatelier's principle, they haven't looked at some things to do with acids and bases. So again, I think it's quite nice to teach that towards the end of the course and relate it not only to other parts of the syllabus too, but also to things which are major environmental concerns as well. So let's have a look at a few other sort of anomalies in the syllabus and to do with the teaching order, etc. And another one, this is basically just for higher level, but basically where we teach the connection between Gibbs energy and equilibrium. So this is something, this is new, this equation relating the Gibbs energy to the standard Gibbs energy and the reaction quotient is a new equation for the syllabus. And on the syllabus, it's been put in the entropy and spontaneity section, but before the students have met equilibrium, before they've met reversible reactions, and definitely before they've met the reaction quotient. So I think it's actually would be very difficult to teach at that stage. And to me, it makes much more difference and much more sense to slot it in to the equilibrium chapter and sort of relate it then to the reaction quotient and the other stuff they've done on equilibria. And a similar sort of thing where to teach fuel cells. Now, fuel cells, obviously this is a nice topic to be talking about at the moment, with the possibility of hydrogen-powered cars and everything. But to actually understand and explain how a fuel cell works, I think this goes much better in the section on redox, when the students have done voltaic cells and they've looked at some of the theory behind that, rather in the section which is more to do with combustion of fuels and alternative fuels. So I think I will be teaching it much more in the redox section there. And then talking about redox, and redox is one of those topics which on the new syllabus is aspects of it appear at quite a few different places, and oxidation state appears in the section 10, which is mostly to do with the periodic table, but oxidation states are introduced at that stage. And there is some rationale for that. It's because we're talking about variable oxidation states in perhaps the oxides of some of the elements, or we're talking about transition metals if we're doing higher level. But again, I think oxidation state, it fits in much better with the other stuff on redox. So that will be something I'll be saving for a bit later, perhaps mention it early on in the course, and just with regard to sort of iron 2, iron 3, or sulfur 4 and sulfur 6, but then talk much more about it later on with all the rest of the redox material. And then a topic close to my heart is organic chemistry. This is one of the fun bits, teaching organic chemistry, not always from a student's point of view, but there's lots of good things to understand in here. And the organic is one of those topics which is split up quite a lot on the syllabus. We start with section 11, which is basically introduction to organic chemistry, naming, general structures, recognizing functional groups, and then there's some stuff on spectroscopy as well. Then we get all the way to section 21, and then we're looking at radical reactions. And then section 22 is the vast majority of the organic reactions. But we have a couple of anomalies in there. So polymers are introduced in section 9 of the syllabus, which is all to do with materials, and so from bonding to materials. And on the standard level part, we've got addition polymerization, but then on the higher level part, we've got condensation polymerization. And I think it would be very difficult to teach condensation polymerization, formation of polyesters and everything, without having been introduced to esters in section 11 first. So I think that's very much one I'm going to try and keep with the rest of the organic chemistry. And then there's a couple of bits on redox reactions in organic chemistry in section 20, which the rest of that is all about redox reactions. And again, you may want to teach with that section because you could sort of look at some of the overall redox equations for reactions of oxidation of alcohols or things like that, so you can relate it to that. But I think it's quite nice to come back to it in the put it all together with the rest of the organic chemistry, and then come back to some of the redox equations there, and then relate it more to changes in structure, changes in functional group in organic chemistry. Okay, so the new syllabus as a whole is described as concept-based, which is something I think is a good thing. I do enjoy teaching the concepts of chemistry, getting the understanding, trying to get the students to understand chemistry in terms of a few basic principles. So I think that's a very, very positive thing of the new syllabus. But I think it also introduces challenges. I hope it doesn't make the exams too much more difficult, because obviously if something is concept-based, I think it does require a lot more understanding from the student's point of view, and they're not picking up then marks perhaps in the exams through just reciting a little bit of learning or whatever. So I think there could be challenges there. But I think one of the big challenges of concept-based teaching from this point of view is to still relate it to chemical reactions. And I think chemistry very much is a practical subject, and I think we lose something if chemistry just becomes something we do on the board, and we just seeing chemical reactions on paper, but not actually sort of seeing the reactions as they happen in a test tube, in a beaker or whatever. And I think one of the things I'm very much going to look at with teaching the new syllabus is to bring in as many chemical reactions as possible. I like doing demonstrations. I like showing the students an illustration of a point and how something works with a chemical reaction. And I thought I'd tell you about one of my favorite demonstrations today. And this is a very, very simple demonstration. It is basically just there to illustrate the reactions of saturated or unsaturated organic compounds with bromine water, test for saturated or unsaturated. And what I do is I use cyclohexane and cyclohexene and mix each one separately with bromine water. And the first thing, so I'd get the students to talk about with this is, why am I using cyclohexane and cyclohexene? Why not ethane and ethene? And hopefully they realize then, okay, these are sort of bigger molecules. They've got higher MR. So we've got stronger intermolecular forces. So these are going to be liquids at room temperature. And it's much easier to do the demonstration with liquids. So the first thing, so we're bringing in a bit of bonding there as well. And now we've also got a chance. It's okay, I haven't chosen hexane and hexene. I've chosen cyclohexane and cyclohexene. So what are these? These are ring compounds. And okay, so what do these ring compounds look like? What does a molecule of cyclohexane look like? And although sort of conformers are not on the new syllabus, they were on the one we're still teaching at the moment. I think it's quite nice to talk about the shape of cyclohexane in here, the chair and boat forms, and also to talk a little bit about VSEPR, how VSEPR can show this shape of a molecule around a particular atom, but it's not going to tell us the most stable conformer for a molecule, the most stable conformation of that molecule. So again, we're bringing in a bit of bonding there. But anyway, on to the actual demonstration. So the first one is nice and easy. I start with cyclohexene, add some bromine water in a boiling tube or a test tube, and shake it up. And as you can see here, this is a sort of picture from the current book, and the bromine water is decolorized. And again, this is quite a nice thing with getting the students to describe what's happened, because one of the words the students tend to use when they're describing this, they will say the bromine water has gone clear. And this is quite a good opportunity to explain the difference between clear and colorless, where the bromine water is clear, you can see through it, it's not cloudy, but it doesn't, and it stays clear, whatever happens, everything is clear in this reaction. But then it is decolorized, it goes from orange to colorless. So understanding the difference between these two terms. So that one's nice and easy, illustrates a point, and then we come on to cyclohexane. So I do the same thing with cyclohexane, shake it all up together, okay, and ask the students what's happened. And without fail, they'll say nothing's happened. And so I say, okay, are you sure? Okay, so let's do the reaction again. And this time I want you to look very carefully at what happens. So I shake it up again, okay. And what we've got is, this is not an actual photograph of what happens, it's one I played around with a little bit, but basically then it's getting the students to realize something has changed in the reaction mixture, because the orange color, whereas it was at the bottom, is now at the top. So this is what can lead on now to a discussion of the scientific method. So the first thing we've got is we've made an observation. So how now do we relate this observation? So where do we go with this observation? So the next thing we're doing, if we're proper scientists, the next thing we're going to be doing is, can we come up with a hypothesis for this? Can we come up with an explanation? What has happened? Why has the orange color switched places? And the first thing the students come up with, of course, is that the bromine water has just switched positions. So the bromine water was on the bottom, it is now on the top. Okay, so we have a hypothesis. So the next thing a scientist would do with this is they would try and test this hypothesis. So how are we going to test this? And this usually takes a bit of discussion to come up with a fairly simple method of doing it. But eventually we come up with the idea, okay, we want to find out where the water is. So if it's switched positions, we're now saying the water is at the top. How could we check that? Well, one thing we could do is we could add some water and see whether the top layer gets bigger or the bottom layer gets bigger. And of course, it's the bottom layer that gets bigger. So the water is still on the bottom, but the orange color is on the top. And then we have a bit more discussion. Can we come up with now a different hypothesis to what's happened? Can we try and figure out what's happened? And then again, we eventually get there. Okay, so bromine is non-polar, cyclohexane is non-polar, and perhaps bromine is more soluble in cyclohexane than it is in water, which has got hydrogen bonding and is polar. And so eventually we're getting to this idea that this is to do with solubility. And again, we're relating it to intermolecular forces, some of the stuff they've done in the bonding topic. And so bringing in something from there. And it also allows, with a new syllabus, there's a bit more on separation techniques there as well. So they're looking at solvent extraction. So this can be related to solvent extraction. And there's a bit on the theory of chromatography as well. So we're related to partitioning chromatography. And beyond that, sort of looking at the scientific method, linking it to other parts of the course as well, we can also talk a little bit about language and how precise we have to be with language. And for instance, in this reaction, is it okay to say that nothing's happened in this reaction? Is that the answer that's required on the exam? Is when we shake bromine water with cyclohexane, nothing happens. because something has happened, and so it's just sort of to get the students thinking about sort of, yeah, in the exam, do you actually have to write, what would you actually write in the exam? And of course, I always advise them, you write in the exam, nothing happens, the bromine water is not decolorized when you shake it up with cyclohexane. But of course, the student, you know that something really does happen with that. And there were lots of links in what I've talked about there with that little demonstration, and that whole demonstration can actually take a whole lesson. There's so much to talk about with regard to it, but the idea of linking it to other parts of the course is a very big thing on the new syllabus, and there are linking questions throughout the syllabus, and teachers are also encouraged to think of their own linking questions as well. And throughout the textbook, as I've tried to sort of link as many different parts of the course together as I can. And this is a great way of sort of teaching chemistry and getting students, giving students the idea that all of chemistry sort of links together. Yeah, sort of. I found when I was doing chemistry at this level, it was sort of April of that second year was by far the best bit of chemistry, because I could see the connections between all the different areas of the syllabus. And that's what we're trying to hopefully get the students to experience as well, that all of chemistry fits together, and we can link different bits of the syllabus together. And it's not just about linking things within the syllabus, it's also good to link chemistry to the wider world. Of course, chemistry is inherently interesting, and it's great doing chemistry just for the sake of it. But it's also nice to relate things to the chemistry to things that students are familiar with from everyday life. And throughout the textbook, I've sort of tried to provide some ideas for this. What we've got is a feature called Science in Context in every chapter, where I've tried to sort of put a real emphasis on environmental things as well, because environmental stuff is something I'm interested in, the students are very interested in at the moment, but just trying to link chemistry to everyday life. And of course, we're also trying to link chemistry to nature of science and theory of knowledge. And the hybridization one here, the theory of knowledge one, is something I really like talking about. Obviously, this is a higher level only topic, but hybridization is something that students find quite challenging. But eventually they get the hang of it. They can work out if you've got the nitrogen and ammonia, it's sp3 hybridized, and they're quite pleased with themselves. And then you start challenging them. So is hybridization actually real? And that always throws them a little bit. So why would we be learning this if it's not real? But it's really good to think about why we have hybridization, why we've invented the idea of hybridization, and gets them thinking a bit more beyond just the straightforward chemistry syllabus. And also with the hybridization part, it's good to look at some of the IB questions. So I'm not sure they always approach hybridization from the right direction, and get the students thinking about, do we talk about the shape of the molecule first, or do we talk about the hybridization? And I think a lot of the IB questions tend to, there's an implication that the hybridization is coming first and then the shape, whereas I think it should be really the shape first and then the hybridization is a way of explaining it. So it's good to get the students sort of looking at that and sort of looking at IB questions critically as well. And the last bit is just how I go about teaching IB chemistry. I hope you've got a flavor of that from some of the things I've said already, but I'm a great believer in practice, and sort of teaching the concepts, the students learning the concepts, but also doing an awful lot of practice on those concepts. And I tend to set my students an awful lot of questions, and I want them to do some repetitive practice, just getting used to recognizing patterns, getting the way of doing questions embedded in their minds. And so throughout the textbook, I've tried to, on this third edition, especially, I've tried to increase the number of questions. They're now called test your understanding questions, and just give the students as much practice as possible on all the different bits of the course. And then at the end of each chapter, there's a link to exam style questions. So sort of some more involved questions, possibly also involving different parts of the syllabus. And this is now in the digital material that goes with the course book as well. And so some extra practice for students on those as well. Right, so I think that's very much my part, that part of the webinar. I end with a lovely picture of Cambridge. I've punted along that river on many an occasion. I've also fallen in on a couple of occasions as well. It's not the cleanest water ever, but basically, so I hope you enjoy that lovely picture of Cambridge, and it's over to Tamsin again.
Brilliant. Thank you so much, Steve, for that fantastic presentation. Very much appreciated. Now, let's move on to the question and answer session. Lovely. There we go. Brilliant. I've got some questions coming, but please do keep adding them. Okay, so let's go with our first question here. So this was started from our kind of teaching challenges conversation at the beginning. Kate here asks, my concern is around teaching explicit conclusion and evaluation skills for IA sections. Do you have any advice, please? And thank you.
It is very difficult. Yeah, this is by far the hardest part of the IA for the students. These are very sort of high level skills to get them used to. What I tend to do is I do a practice IA, so a fairly simple experiment. I'll do a rates experiment of some sort, and then get the students to write this up, and concentrating. We concentrate on the different sections each time. So I get them first of all to do an exploration part, then we'll write up the analysis part, then we'll do the conclusion and evaluation. And then for each of these sections, what I tend to do is then talk through some of the things with regard to that. But actually realizing what has gone wrong with the experiment, evaluating the experiment, is actually quite a difficult thing. And what I tend to say to the students, right, what we're really looking at is we're looking at, do you believe your conclusion? So your conclusion is going to be, usually have two parts to it. It's usually going to have a qualitative part as X increases, Y increases, and then you've almost certainly drawn a graph, and then you've got the quantitative part of that. Now, what evidence do we have that you can believe either of these two parts? And the first thing, okay, with the qualitative part, okay, we can look up some background theory. Does it agree with background theory? Does it agree with what everybody else has found? And we usually get to the point where, yes, I can be pretty confident about the qualitative part of my conclusions. X increases, Y increases. Everybody else in the world has always found as X increases, Y increases. It agrees with all the scientific theories that exist at the moment. So I can be pretty sure that that's absolutely fine. But what about the quantitative part of this? So you've drawn a graph, you put the equation on the graph for that, and do you believe the numbers? And the usual answer you get from the students, oh, no, I don't believe the numbers. So why don't you believe the numbers? Okay, so you might be right. This might be the exact mathematical relationship between these two quantities. And it's all about trying to get them to think critically, sort of, okay, so what sort of evidence do we have to make us believe the numbers or not believe the numbers? Obviously, if we can find somebody who's done the same experiment before, so is there a literature value for this particular quantity? Can we compare our value to the literature value? Or what if there isn't a literature value? Okay, so how do we make the decision then? And of course, that gets more difficult. So then we say, okay, right, what evidence we have from the data? Is my data any good? Do all the points lie on the line of best fit? Is the repeats close together? Can we identify anomalies? So is my data any good? Can I identify any systematic errors? And of course, the students find it quite difficult sort of identifying systematic errors. So again, giving them some prompts, helping them. So, okay, so yeah, could this be a possible systematic error? Could this have happened? Could that have happened? And then, of course, looking at random errors and uncertainties as well. But I agree, it is a very difficult thing to do, and to have this critical thing is to actually say, look, do I believe my conclusion? I usually say to them, look, if you had to stake your entire scientific reputation as it is at this stage on the conclusion of your experiment, would you do so? And that's what you're talking about when you're concluding, when you're evaluating, is why I would or I wouldn't do this. Okay.
Brilliant. Thank you, Steve. Our next question asks, can you tell me the list of practicals for this new syllabus?
There is not a list of practicals as such. There are some things that students need to do. So on the syllabus guide, there is a list of some practical tools students need to be able to do. But these are things like doing a titration, recrystallization, and things like that. So there are no actual set practicals, but there are practical techniques that the students should be doing. And so it's a bit more vague. So it will be a case of the teachers sort of coming up with their own practicals to illustrate these particular points. And things like recrystallization, it's an interesting one. It's not a sort of quick thing to do. Generally, sort of usually doing recrystallization as part of a sort of longer sort of organic practical. So I was thinking perhaps at some point on the new course we might make aspirin, which is not too difficult, a practical, and then recrystallize the aspirin from that. But with regards to practicals in general, there is a list at the beginning of the syllabus, but it's quite vague, so it doesn't sort of give too much detail there, but rather some ideas.
Great, thank you. And next question is about, please could you discuss ATP teaching?
Could you tell me what ATP teaching is?
Simran, if you'd like to add a clarification to the chat, we'd love to see it. We're going to just jump on to the next question while you add your clarification to the chat, and I'll pick that up in a moment. But the next one is, so are all the options going to be integrated into the new course syllabus?
No, basically there are some bits of the option in the new syllabus, but only a few bits. So if obviously with 4 options previously, the content would be way too large if they incorporated all of this. There are some, I would say most of the bits that are in there come from option A and C. There's some bits on materials, there are some parts on the environmental stuff, and there are 1 or 2 bits then from the other options as well. They are mentioned as well, but there's only a few of the bits. So most of the material is what was on the core before, with a few bits from the options incorporated, and there's a couple of sort of brand new bits as well in the syllabus as well.
Great, thank you. Now the next question. We used to aim 6 for experiments. What's it going to be now?
So could you repeat the question?
So we used to aim 6 for experiments. What is it going to be now? Or how is it going to be now? Do we think we need a bit of further clarification on that one?
I don't understand. Yeah, I'm not sure what the question means.
Javita, if you could add to the chat as well. And we're still just waiting for Simran, if you'd like to tell us a little bit about ATP teaching, and then Javita, if you could explain a little what you mean about aiming 6 for experiments, that would be great. Thank you. Okay, so our next one. Hello, I am a new IB teacher. Could you please give some idea regarding TOC, IA and practicals? So I guess your top tips for those, little explanation around them.
I think with the TOC, it's basically, find a few sort of areas to sort of talk about that. I do try and bring it in when I can, but I wouldn't worry too much about sort of bringing in all the time. I don't need to bring it into every single lesson. I talk about it very much from the first time I sort of introduced it with the students. Is basically it's connected to IAs as well. When we're first talking about measurements and when I sort of say to the students is there is no such thing as an exact measurement in chemistry and science. And although we talk about exact sciences, is we can never measure anything exactly. So and then you can later on the idea, okay, from science, then can we know anything exactly? Because everything has an uncertainty associated with it. So that's quite a good introduction to sort of doing the TOK in there, and also to start to talk about IAs. The IAs is quite a big thing. So there will be teacher support material coming out from the IB. I think that will be published in September. In the digital content, I've also, for the course book, I've also done a guide to IAs as well. And as a new teacher, this is something that does take quite a bit of learning, and it is very important to understand the criteria and to be able to teach your students the criteria as well. So I would really recommend going through that and getting as much advice as possible on the IAs. And I used to do quite a few years ago, and I used to do quite a lot of IA moderation for the IB. And that the main problem there with some of the practical work we were getting was where the students weren't understanding the criteria, because I think the teachers didn't understand the criteria. So it is really important. And I teach whole lessons to the student on the criteria for the IAs. I go through each of these and just try and explain all the criteria. So it does require quite a bit of practice. And what was the third part, Tamsin, as well?
And practicals as well was the third part.
Practicals as well, okay. Sorry, but yeah, so with practical work, obviously chemistry is a practical subject, so it's good to try and incorporate as much practical work in as possible. Obviously, it depends on what resources you have available to you in your school, etc. But I think the teacher support material from CUP will have ideas for practicals and everything in there as well. So I think that will be a valuable resource. And it's written by two people I know who are very experienced IB teachers who've had a lot of experience teaching IB chemistry. So those will be some good ideas for practicals. But do look at the IB syllabus. I said the things that are mentioned on there, they aren't specific practicals, but they are tools that the students will need to have, and that will be important when they're looking at paper 1B in the exam, which will relate to practical work as well. But good luck. It is a fun course to teach. I said I've been doing this for about 26 years now, and it does take quite a bit of learning, but as you go through it, I'm sure you'll do a brilliant job. So but good luck on the journey for that one.
Great, thank you, Steve. And yes, I was going to mention our digital teachers resource, and you can see links to our resources that I've been putting in the chat with my colleagues as we went along the way. We did actually have Simon come back to us saying ATP is alternative to practicals. So what are the most important practical techniques that an O-level student must be taught? But that's kind of out of our sphere. That's more to do with presumably IGCSE and the alternative practical paper.
Alternative practical paper and everything.
Okay, right. Let's see our next question. Is it good practice to teach HL and SL separately?
Yes, if I know it's a difficult thing. I know some schools this is not possible where they have smaller classes and everything. But I think it is very much the preferred option to teach SL and HL separately. They are very different things. There is a lot more material in the HL part of the course, but I've never had to do it myself, but I know I have talked to people who have had to do it, teaching everybody together, and it is quite difficult. So I would say yes, if at all possible. Try to convince the school management to allow sort of teaching of that separately. because they are very, very different things. And there's much more quantitative material in the high level syllabus. And I do tend to talk to the high level students differently, to the standard level students differently, in the way I tend to go off syllabus a little bit, and just to sort of extend them a little bit as well.
Great, thank you. Another question about practicals here. How many practicals should be performed for DP students?
You're looking at, I'm not sure whether the syllabus has got the same sort of recommendation of thing, but we usually look at high level, it's about 50 hours of practicals, and standard level about 30 hours of practicals going through the course. And then you've also got the IA on top of that as well. So yeah, it's finding the time to do it, and it's basically what you count as a practical as well. So it doesn't necessarily always have to be a lab-based exercise where people are using apparatus in the labs. It could also be a data-based exercise, is processing data for something like that as well. But you are really looking at it, quite a bit of practical work in the, if you're looking at sort of over the 2 years of the course, we're looking at spending perhaps sort of an hour every couple of weeks doing practical work. And it is an important part of chemistry. You know, if they go on to, we're trying to encourage our students to perhaps go and do chemistry at university level, and obviously there you're spending whole days in the labs and everything, so it's getting used to that as well. But yeah, so aim for about 30 hours and 50 hours, I would say, going through the course.
Brilliant, thank you. And can I just mention to you, Simran, that talking about Cambridge GCSE, we have a lot of materials on our website, webinars and blog posts advising about practical work, etc., in relation to Cambridge GCSE sciences. So I will make sure I include those in the email out that everyone is going to get in 7 days' time as well. So we're covering everything there. Now, the next question is, the current course feels difficult to fit into the timing due to its size. Do you get the impression that this version is any smaller in scope? Giving enough time for practical experience building up to the IA is the aspect we found too tight in the current version.
Yeah, it's I think this is always going to be a challenge. I find it more of a challenge at standard level than higher level, and it is very, very tight for time at standard level. At higher level, it's usually not too bad, but I agree, is getting the practical experience in there, getting the students to have learned enough chemistry before doing the IAs is quite a challenge. And of course, it all depends where you do the IAs. We tend to do it towards the end of the first year of the IB. My students have just been doing it now over the last few weeks. But of course, if you leave it a bit till the second year, you've got a bit more time to fit in some more practical work. But I think this new syllabus will be quite tight for time as well. It all depends again as how in the past you've taught the options as well. I know some schools they will very much allow the students to go away and try and learn the options themselves and sort of give them some material, but also encourage them to do some research on the options. But without the options as a separate thing, then there is perhaps more content to cover in the classroom as well. So yeah, no, I do take your point. I think it will be quite tight for time. And standard level, again, it's going to be a challenge. But the practical work at standard level as well, I agree, is just fitting that all in and getting a sufficient experience before they're doing the IA is difficult.
Great, thank you, Steve. Now on to our final question. So if there is only one student in IBDP, how do we conduct activities?
It's not a problem I actually encountered. I usually have a class of 15. Yes, okay. Well, you won't have many collaborative activities, but I think you can still do quite a lot of practicals. I tend to do at this level is I will usually get the students doing practical work by themselves anyway. Tamsin was mentioning IGCSE. I also teach IGCSE. At IGCSE level, we tend to have the students doing practicals in groups. At IB level, I want the students to learn a bit more independence. and to be able to do the practical work themselves. So I don't think there's too much difficulty there with the practicals. I think it will be a challenge to do that with just one person in the group is getting any discussion going. It's the demonstration I was talking about there, that could be quite difficult with just one person and everything as well. So I'm not sure I have too much advice on that one. I'm used to much larger classes, and which can present their own problems as well. So we are actually doing IAs with about 120 pupils, which creates quite a lot of difficulties as well. But with one pupil, I think getting them to do the practicals by themselves is quite actually a good thing, and they will learn a lot of independence. They will learn a lot of good practical skills through doing that as well.
Brilliant. Thank you, Steve. So that is everything from the questions today. And thank you again for your fantastic presentation. And thank you everyone for attending today and taking the time. Remember that 7 days after the webinar, we'll send you an email thanking you for your attendance with a link to the recording of the webinar and the webinar slides and all the links we've been sharing today and the links I just mentioned with some Cambridge GCSE material as well. So this email that you get, you can use this email as proof of your attendance. To find out more about the resources discussed today, you can speak to your sales representative or visit the links we've just been sharing in the chat. Thank you to Michaela and Georgia for helping us today. When the webinar ends, a short survey to complete will open on your screen. So thank you for any answers you provide for that. So good luck with your teaching and goodbye.
Bye-bye. Bye-bye. Good luck. Good luck with the new syllabus.